Here's a graph of the standard normal with standard deviation 1, mean of 0, and its associated distribution function. And one sees that the distribution function, which formally, of course, is defined from z equal minus infinity to plus infinity, but one of the familiar properties of the normal distribution is that once you get beyond 3 standard deviations, there's very, very little probability mass outside of 3 standard deviations in the normal. And so for all practical purposes, if you go from, say, 4 to minus 4 to plus 4, you have all but a de minimis amount of probability mass. And the distribution functions, of course, always begin at 0, at minus infinity, or the leftmost probability value, the leftmost random variate value, and they increase. They're non-decreasing functions, technically, but typically one sees an increasing function, and it ultimately ends up at 1, or it's asymptotic to the value of 1 as the random variable z, in this case, increases to infinity. And so we see that the connection between area of the probability density function and the functional value of the distribution, namely that if we pick this particular value of c, the example shows the area is equal to about 0.62, and that's precisely the value for that z value on the cumulative density, cumulative distribution function. It's also common when we're working with the normal distribution to be interested in confidence intervals or probability intervals, where we're in fact interested in the probability that the random variable is in between a value A and a value B. Sometimes we're interested in the symmetric interval around 0, which would be from minus A to plus A. Sometimes we're interested in a symmetric interval around the mean, so that might be from mu minus A to mu plus A. And there are times when we're just simply interested in an interval that goes from a number A to a number B. So in this, we're going to look at this example of where we're looking for a symmetric interval for the standard normal between minus A and plus A. So, of course, now here's an example of where perhaps the author was a little bit careless, but you notice that we're defining here that n of minus A is the probability that z is less than minus A. Again, technically, we should have the equality, but note that for the continuous normal distribution, it doesn't make any difference. But just to be in the habit of putting the equality there, because it certainly does make a difference for some probability functions. Similarly, the probability that z is less than or equal to A is defined as n of A. So if we're interested in the probability that z is in between minus A and plus A, well, it's just the difference between these distribution function values. And because of the symmetry of the normal, the probability that z is less than minus A is the same as 1 minus the probability that it's less than A. And the symmetry that we're looking at, if we think about it just for a moment, is here's minus A, and here's A. And what we're really saying is that the probability that we're less than minus A is really the same as the probability that we're bigger than positive A. That's the symmetry property. Well, the probability that we're bigger than positive A is 1 minus the probability that we're less than positive A. And we do the math, and we finally get 2n of A minus 1. So we can express a symmetric interval about 0 in terms of 2n of A minus 1, n of A conveniently being a value you could easily look up on a typical probability table, so this is convenient. It tells you that if you're looking for symmetric intervals around 0, you can just do a lookup in a typical probability table, double it, and subtract 1. And of course, if your probability table goes from 0 to A, you must first add a half to its value before you double it, and then subtract 1. So in this example, we see that looking at the slide earlier, where we already know the probability that Z is less than or equal to 0.3, we see that in that example, the probability that Z is in between plus and minus 0.3 is roughly 0.24. So this formula that the symmetric interval is equal to twice n of a minus 1 can also be expressed geometrically. If we just look for a moment and imagine that we have two normal distributions. And we have an A in both. And of course, what's n of A? N of A is an area to the left of A, by definition. And so what this formula that we just saw says, that the probability that we're in between A and minus A is 2n of A minus 1, is basically saying what's 2n of A? Well, here's 2n of A. It's the sum probability of what's under two normal distributions. And then if for a moment we take the left curve, and what we're going to do is remove the left tail at minus A, and we're going to move that probability to the right tail of the upper distribution, the right-hand distribution. You see what happened. When we have 2n of A, all we have to do is move the left tail of the left distribution into the right tail of the right, and we see very easily that 2n of A is exactly equal to the probability we want. And what's on the right now is a full distribution has probability 1. And that's all that formula is saying. It's just a simple consequence of the symmetry of the normal distribution.